This is the second lecture looking at the learning outcomes associated with 1.1 controlling the rate. In the first lecture we looked at reaction rates, and in this lecture we're going to look at potential energy diagrams. The first learning outcome is that you should be able to calculate activation energy and enthalpy change from energy profile diagrams. So here's a potential energy diagram showing the energy change as you go from reactants to the products. So the activation energy, and here we're talking about the forward reaction, which is going from left to right in the diagram. So going from, in this case, the reactants to the products. So we're talking about the activation energy for the forward reaction. It's just forward reaction going in that direction. So the activation energy is from where you start, which is at 30, to the highest point, which is 40. So that was the activation energy for the forward reaction. So it's 10 kilojoules per mole, and going up the potential energy diagram is always positive, it's always endothermic. So EA is plus 10 kilojoules per mole. If you don't put in the plus sign, it is assumed to be plus, but I think it's always better to hesitate and think, is it positive or minus, and put a sign in. Okay, what about the enthalpy change for the forward reaction? Well, the enthalpy change is delta H, and it's difference from where you start to where you finish. So that's that distance there, that's delta H. So we start at 30 and we end at 10, so we've dropped by 20. So this is an exothermic reaction. Products have got less energy than the reactants, so the energy change is minus 20 kilojoules per mole. Okay. We can also work out the activation energy and the enthalpy change for the reverse reaction. So the reverse reaction would be going in that direction, going from the products to the reactants, in which case the activation energy, well, we're starting here, the highest point is there, so that's the activation energy for the reverse reaction, which would be going from 10 to 40, so it's plus 30 kilojoules per mole. Delta H for the reverse reaction is from where we start to where we finish. So the magnitude of delta H is the same for the exothermic and endothermic. It's just the sign that changes. So we're going from 10 to 30. That's delta H for the reverse reaction. So it's plus 20 kilojoules per mole. Okay. So make sure you can work out activation energy and enthalpy change for the forward and reverse reactions from potential energy diagrams. Here's another one. This shows the forward reaction being endothermic because the products have more energy than the reactants. So we'll just do the forward reaction in this case. So for the forward reaction, so that's going in that direction, the activation energy, so from where we start to the highest point, so it's gone from 50 to 250, so it's plus 200 kilojoules per mole. And the delta H value from where we start to where we finish, so it's that change there, 50 to 100. It's going up the way, so it's positive, so it's plus 50 kilojoules per mole. The next learning outcome is to be able to show the position of the activated complex on an energy profile diagram. So the activated complex is at the highest point of the diagram there. Then the next related learning outcome is to know what is meant by the term an activated complex. Right. The activated complex at the top of the potential energy diagram relates to this species here. It's the unstable arrangement of atoms, which is a halfway point between the reactants and the products. When you reach the activated complex, this is unstable and will break down. It can break down in such a way that you go back to the reactants, or it can break down sometimes in such a way that you go and make the products. The size of the activation energy relates to the size of the collision required between the reactants in order to make the unstable activated complex. You should be able to show the effect of adding a catalyst on an energy profile diagram. So here's a reaction. Let's say it's quite slow, we want to speed it up, we want to use a catalyst. Well, the things to remember is you start off at the same point, you end at the same point, you just reduce the activation energy. So the blue line there could represent the effect of using a catalyst. You've reduced the activation energy from 10 to 5, hence making it easier for the reactants to form the activated complex, hence increasing the speed of reaction. So just make sure you start at the same point, end at the same point, you just don't go quite as high. So you provide an alternative pathway for the reaction.